Okay, so yesterday, this was the last result I presented. It is a theorem that I proved with Emilio Scendi more than 10 years ago. And this essentially settles the issue of this parabolic nonlinear counterexample signal theory. This essentially tells that the gradient is exactly where data lie sharply, provided this lower bound holds, and this lower bound on P is something that really you cannot get rid of, because as we explained yesterday, then there's no diffusion enough in a very singular case, because what you want to prove here is that after all, the gradient, I mean, it's not really bounded, but there's certain growth in terms of level sets, and so if the gradient grows too fast, then there's no diffusion enough to rebalance the evolutionary effect, and then you create singularities, or in the case the right-hand side is zero. So that's the main idea. So today I'm going to give a sketch of this proof, which involves a so-called maximal function tree proof. Free proof. So there's essentially a proof that involves no explicit tool from harmonic analysis, although some ideas underlying behind these developments and the properties of these tools are actually clearly used all over the proof. Okay, of course I'm going to give a sketch, and during the sketch I'm making a lot of cheating. In particular, there are a lot of concepts. So prior to the beginning of the proof, I have to say something about a very basic idea where you deal with the p-parabolic equations. That's the idea due to Emanuele DiBenedetto and largely developed by him and collaborators in the 80s. So this is the 80s, DiBenedetto, who is in Vanderbilt in Nashville now, and co-authors, collaborators. And that's the idea of intrinsic parabolic cylinders. So as you know, when you deal with the heat equation, so one of the properties, one of the basic features of this equation is that you have several derivatives in space, while you have only one derivative in time. So Bob, I was just introducing the heat equation, and then you appeared. This is a sign, right?
Perfect.
Yeah. This is a sign.
I hope it's a nonlinear heat equation.
At the moment it's linear.
Okay.
It's pretty soon going to be very nonlinear. Okay. Then in order to rebalance the lack of one derivative, you essentially modify locally the geometry and introduce what are called parabolic cylinders. Parabolic cylinders are something that are R in space, so that's the base, and that's the R, so that's the Euclidean ball, and then are R squared in time. So you see, you combine, essentially, you rebalance by a different scaling in time, the scaling of this equation. So therefore, when you make a change of variable, and then you define Vt0, like in B1, like plus Rx times plus R squared T, then this new solution, you see that you have R and R squared, essentially behaves in Q1, which is B1 times minus 1, 0, as this equation behaves in this cylinder. Okay. Now observe that these are the standard parabolic cylinders. Now we pass to so-called intrinsic parabolic cylinders. Now intrinsic parabolic cylinders are parabolic cylinders that are further stretched in time with an additional parameter called lambda. And now, for our purposes, it's better that you think that lambda is very larger than 1. It's very larger than 1. And again, for the sake of simplicity, let me just consider the case p larger or equal than 2, actually strictly larger than 2, otherwise there's actually no content, and no new content here with respect to the usual heat equation case. Okay, so the idea is the following one. Observe this equation and consider a portion of space where the gradient is approximately lambda. approximately means that in a scheme of a very heuristic argument, you can consider that the modulus of the gradient is like lambda. Now, if this is like lambda, then you can put lambda p minus 2 here, and then you can eventually filtrate this outside the divergence operator, and then you get nothing but a heat equation with a different diffusivity coefficient. In particular, if p is larger than 2 and lambda is larger than 1, then you have a lot of diffusion. So, the basic idea, okay, the basic underlying idea of intrinsic geometry is that assume that you are in a cylinder which is of that size. So if lambda is small, if it's large, you have a very much stretched cylinder. So this cylinder gets thinner and thinner. And assume that the gradient is in itself, and this same is like lambda in this portion of space. Then if in this portion of space this is like lambda, then the Laplacian operator behaves like this, and therefore it's like a heat equation with a different diffusivity. But if you have a different diffusivity, then the scaling parameter of this guy is not any longer this one, but you have to do this. So this means that in this very thin cylinder, this equation, and eventually, because of this equivalence, the Laplacian operator behaves as the heat equation. So where does the term intrinsic stem from? From the fact that you prescribe that u is more or less like lambda in a cylinder that depends on lambda, that itself depends on lambda. So that's the meaning intrinsic. So you introduce a parameter, you say for that lambda, in that cylinder, du is like lambda itself. So the idea, this is called intrinsic because you see lambda is simultaneously appearing both in the equivalence claim and in the domain where you're using this. So what's the basic fact, what's the basic advantage of using this geometry is that, yeah?
So I would rather say that the cylinder you want to look at depends on the solution you, so it's intrinsic to the cylinder.
Exactly, right, yeah. That the cylinder depends on the solution. So in some sense, it's you cannot use the intrinsic parabolic cylinders, but you use cylinders that are tailored to the geometry of the solution and of the equation. In some sense, it's a general concept. You have the Laplacian in Rn, and therefore the Laplacian behaves correctly on Euclidean balls. Then you go to the heat equation, and then the heat equation behaves correctly on parabolic cylinders. Then you have these operators, and then these operators behave on these intrinsic cylinders as the heat equation behaves on the standard cylinders. And the same thing you have with sections in Monge-Ampère theory. In Monge-Ampère, you have a very degenerate operator, but then the trick, going back to these papers by Caffarelli and Abiashvili in the 80s, is that you switch to sections, and then on the sections, then the Monge-Ampère operator behaves like the Laplacian. So the idea, and it's the same thing that you also use in homogeneous spaces when you deal with Ormander's operator, sums of squares, Heisenberg groups. You have an operator that is elliptic in some sense. Therefore, you forget about the operator, you locally modify the geometry, and you find a family of balls where this operator behaves in some sense like the Laplacian. So there's a universal concept of ellipticity that is recovered via local deformation of the geometry. This I think that probably goes probably goes back to the first example of this is in the papers of Ormander, actually, because you have the, if you see this very famous paper of 67 by Ormander, where he studies operators that are sums of squares of vector fields, and then he introduces notions of hyperellipticity, then the basic idea is that you get this local intrinsic balls that are defined by the vector fields themselves. So this is just another manifestation of the same general principle. So after all this blah blah, then the basic idea is that if we want to prove this result, we have to use these cylinders. So that's the result. Let me recall you. That's the result we want to give a look at. So, in particular, now you immediately see that if you're using these cylinders, So why are you using these cylinders? Because if you use standard parabolic cylinders, then you don't get homogeneous estimates. If you want to prove regularity results, you have to use homogeneous estimates, because homogeneous estimates can be iterated. If you get something which is not homogeneous and you iterate, this blows up geometrically. That's the idea. So you want to have homogeneous estimates. On the other hand, as yesterday we observed, if P is different than 2, this case like 1, this case like P, and therefore this object is not homogeneous. So the basic idea of intrinsic geometry is to get a local intrinsic family of cylinders that allow you to get homogeneous estimates and eventually to iterate these estimates. So now the basic questions. Are these cylinders making the work they have been devised for? The answer is, okay, the question is obviously clear and the answer is possible. Why? Because there is this warming up result by DiBenedetto and Friedman that tells you the following. Imagine that you are controlling this average via lambda, and now you see the intrinsic condition here is immediately shown by the fact that lambda is appearing both in the domain of integration and on the right-hand side. Then you can control, then you can transform this information in average in a pointwise information. You perfectly know that this is essentially the basic elliptic idea, because the basic elliptic idea...
Sorry, this is for solutions. This is what equation now?
Right-hand side equal to 0.
But the P Laplace heat equation, or
the P Laplace.
No time derivatives. Yes, time derivative. Yeah.
Time derivative. This one.
Yeah.
You know that, for instance, for solutions in the elliptic case, if you have a solution of the P Laplace equation, then you can bound the L infinity norm on a ball, BR, centered at X, by the average B2R. Or call it BR over 2 and BR. In particular, this means that if you have a bound on lambda by this guy, then you have a bound on lambda. And this is transformed exactly in this. So an average, an information in average, transforms into a pointwise information. This is the classical L1 L infinity effect. So this is telling you that the intrinsic geometry allows you to get the kind of homogeneous estimates that are not allowed for the in the standard case if you would use here standard parabolic cylinders. So this is the first sign that these are the right objects you want to deal with. Okay, and now we can give a sketch of the proof. Okay, just let me recall you that the result we want to prove is that we have the evolutionary P Laplacian equation on the left-hand side, and on the right-hand side now you're putting your data in the same form, and then you want to retrieve that if this guy is in LQ, then U belongs to LQ for every Q larger or equal than P. Okay, proving something like this means that you have a bound on the following object. In turn, by Houdini's theorem, this means that you want to control the decay of level sets of the gradient. And now, the idea is that we want to control the gradient of the level sets of the gradient in terms of the level sets of the right-hand side, because the decay of the level set of the right-hand side is known, and therefore you want to retrieve the best possible information of the gradient. So how do you do this? In the classical elliptic case, when, for instance, maximal operators are at your disposal, and this is, for instance, an approach introduced by Caffarelli, Peral, Yoon, Wong, many others, then you do something which is called a good lambda inequality principle, which is, after all, a rather obvious fact. In the elliptic case, you get P Laplacian operator equal divergence of something like this. And the idea is rather simple. Your maximal operators are at your disposal. So instead of controlling the level set of the gradient, you want to control the level set of the gradient of the maximal operator. which is a bit better, because a maximal operator, when you consider a maximal operator, you have a bit of a regularization effect that plays on your side. In terms of the measure of the level set of the maximal operator of the right-hand side data, by the maximal theorem by Hardy and Littlewood, you know how this guy behaves, because if f is in LQ, then the maximal operator of f is in LQ, and after you know how this guy behaves, this obviously control the level sets of that. So that's what you're doing. So the next step is that how do you do this? You say, right. The case which is perfectly fine is when the right-hand side is 0, because when the right-hand side is 0, the gradient is bounded and there's actually nothing to prove. So the idea is to conceive this object as a perturbation of the right-hand side is equal to 0. What does it mean using that it's a perturbation? This means that you trivially rewrite this object in the following way. Sorry, I should not call this a good lambda principle. Let's call it good epsilon principle, because lambda is a level set in this notation. Okay, we say, okay, I want to split where this guy is larger and this is very small with respect to the same scale, plus, well, this is larger than this guy, where epsilon is very small.
So this is a maximum point f larger than epsilon.
Yeah, I think it's better if I rewrite it here, because there's no. Okay, let me rewrite down here. It's better because there's definitely no room enough on the blackboard. So the basic idea is that this is the set you would like to this is the object you would like to estimate. Okay. Then you say, okay. I say when the maximal operator of the U is larger than lambda, and this guy is smaller than epsilon times lambda, so you keep lambda on the same effect, but you say that this guy is very small, plus this guy is larger than lambda. Now for each epsilon, this guy is under control, because it's just a change of variable. Because you know that f, or the maximal operator of f is equal to q, so there's no problem in controlling the decay of this guy. So, and you then remain with the task of estimating this object. But what is the advantage of this object? The advantage is that this tells you that with respect to lambda, this is very small with respect to the gradient. In other words, the right-hand side is approximately 0 if you say that for a certain universal epsilon, the thing is going to work. If you believe that eventually it's going to work, then eventually it is going to work. But what is the basic principle of elliptic equations? Stability. If you solve something with a right-hand side next to 0, you must be close to something which solves really with 0. And therefore, you are able to transfer estimates from solutions to these equations, which are good, to your case. Okay, this is the basic technique that you can, for instance, find in this paper of Caffarelli and Perra. And a related technique with the comparison of maximal operators is in the paper of Ivanitz. All these techniques break down in the parabolic case. Why? Because in order to use maximal operators, you need to have a universal family of balls, and there's no universal family of balls, because the cylinders are intrinsic. So we do not want to use a maximal operators. So we have to find a way to encode information on singular integrals and maximal operators and good lambda or good epsilon inequalities directly at the level of PDs. So the way we found to overcome this is the following one. First time, what do you use in the Calder and Sigmund integrals is exit time argument. So we do directly an exit time argument on the solution and on the data, but weighted at a different level. So we do a direct exit time argument on this quantity when you shrink these cylinders, so there should be an average here, also that you better know, where the U and F are considered at the same level, but M is very large. So this means that if this quantity in average is approximately like lambda, then the gradient to the P is like lambda, but F is like lambda over M. So it's much smaller. And so that's what we do. We pick a point in the level set of the gradient, and then we know for sure by Lebesgue theory that this happens almost everywhere. This is absolutely clear, because this is converging pointwise to the sum of these two guys. Then at least one is larger than one. Then we do the exit time. So we pick the first radius such that this is exactly like lambda in average. So what does this mean? And then we cover Vitalli or Bezigovic is the way you like. So you extract the covering of the level set with these balls, and these balls, are these cylinders, they have the magic property that this average is like lambda. But be careful here, because these are not usual cylinders, these are intrinsic cylinders. So the idea is that for each lambda, you consider a different family of cylinders, so a different metric in R to the n plus 1, and this metric is, has these cylinders. And then you do the exit time with respect to these balls, to these new cylinders. So essentially, these intrinsic cylinders are cylinders with respect to this metric. So for each lambda, you make a different covering and a different exit time using those intrinsic cylinders. Okay, what's the magic effect? The magic effect is that this means that if the U is more or less like lambda, then this is much smaller than lambda if you take M large enough, and this will be done very eventually at the end of the proof. And on the other end, you have a double control. So this is what you get. So for each level, you define a metric, you take a family of cylinders, and then by exit time, you choose the cylinders in a way that they are intrinsic. That is, this relation is satisfied. You take lambda, you take a metric, you take a family of cylinders, and then by exit time, this cylinder, you extract the covering of cylinders that are now intrinsic cylinders. Okay, and now on each one of these cylinders, we want to reproduce the scheme of the good epsilon inequality. Why? Because on these cylinders, you know that the gradient is more or less like lambda, but this guy is much smaller than lambda. Because it's lambda over m, and eventually you want to know that you can choose m large enough independently of everything that makes everything on the right-hand side small. So on each one of this cylinder, you solve the Cauchy-Dirichlet problem, made as follows. So you take a right-hand side is equal to 0, and on the boundary, on the lateral boundary, on the parabolic boundary of the cylinder, that is the base plus the lateral boundary, you put the same data u. Therefore, it's not difficult at this time to prove that since the initial energy of the U is bounded by lambda, this guy more or less decreases the energy up to a constant, and then this is bounded by lambda. Moreover, what's the difference between the original equation and this equation? It is something that depends on f, but f is bounded by lambda over m, therefore also the difference is going to be small. And now the idea is that you want to transfer the good properties of V to U on every one of these cylinders. Okay, and now you use the magic property of intrinsic cylinder. If on an intrinsic cylinder you have an information in average, then this information in average transforms into an information, a pointwise information. So this is the information in average, and this is the pointwise information. But this you see, you do not lose any exponent here. If this would be a normal cylinder, you would get lambda to some bad exponent, like for instance p over 2 definitely, and you would lose the possibility of iterating again. But since you are in intrinsic cylinders, then the same exponent is preserved by the homogeneity of the a priori estimates available for solutions to these equations when you're dealing with intrinsic cylinders. Okay, now you have this soup, and this means that, of course, the level set disappears after a while. These are completely equivalent. Of course, there's lots of cheating. This means that there are constants appearing everywhere, and you have to you have to control the constants. But that's the basic idea. Okay, then you know that everything is going to be fine for B, I, and then we transfer this information to du. We say that du is like this guy, and the difference. But this guy is not there, because this disappears, so you just keep the difference. Then you do Chebyshev, and this is trivial, but the difference is small. Surprise, surprise, what did you get? You get the Giorgi density type information. You say that on each one of these cylinders, the density of the level set is very small. It's 1 over n. This is the typical kind of the Giorgi's density information. The whole theory of the whole scalar theory of the Giorgi is based on the fact that when you have these informations, then you smooth out completely the level set on a larger level. Okay, how do we conclude now? We conclude by using the other inequality, because we do not only know that this quantity is less than lambda, we also know that this quantity, let's say the composite quantity, on the same cylinder was larger or equal than lambda. And we know then the density of the level set is now very small. Now, what is this? It's 1 over qi. So we switch this here and this here, and then we get this. Because that's the double control. We didn't use up to now the lower bound. We just used the upper bound. The upper bound was used to get smallness and a priori estimates. Now it's time to get a control on the measure. Yeah?
Sorry, the first line, QR does not become lambda.
Oh, it's Zi. It's Zi and lambda. That's a double typo. Thanks a lot. I will definitely fix this into. Okay. So this is what we know. And now we combine this information, because we know that the density of this set can be controlled by this guy, but this guy can be controlled by the integrals. This is just a combination of these two inequalities. But we all know that these balls are, let's say, covering the level set. So we can multiply everything by lambda and integrate. And now, surprise, surprise, du to the p gamma is like this. This can be covered by this. And now you will see the magic effect of the good lambda inequality principle, or the good epsilon inequality principle transferred directly on this exit-time approach via double-weighted level set. Why? Because now this is exactly due to the p. This is exactly f times a constant that depends on m. And now, surprise, surprise, this is this guy estimated by this guy. That's the estimate you want. And there is still this guy. But now, if m is large enough, you can reabsorb this guy on the left side. This module, a lot of technicalities. For instance, you need a truncation or an approximation argument. Why? Because you cannot reabsorb something that eventually you want to prove to be finite. This could be infinite. But this can be eventually fixed by an approximation or a truncation argument. We are proving that this object is finite, but we are proving that it's finite by reabsorbing itself from the right to the left-hand side, which is clearly forbidden. But this can be fixed. I mean, once you have a good a priori estimate, then the a priori estimate can be overcome by the fact. And that's essentially the same idea of the proof. So the proof essentially encodes the ideas behind singular integrals and this maximal operators approach, but without using maximal operators. You are directly making coverings, exit time arguments, and good lambda inequality type principles, but done directly at the PD level. And this, of course, because you want to get rid of the use of maximal operators that are simply not available, because you see at each stage here you are dealing with intrinsic cylinders. And intrinsic cylinders are not good to build maximal operators. I mean, there are objects controlled called universal maximal operators, where you have where the sup over all averages is taken over all possible rectangles. These control the equations, but the equations are not controlling these operators, so it doesn't have balance. So you have to go directly to the point. So the pleasant outcome is that the same proof can be then applied to the usual elliptic setting and provides you a very fast proof of all the usual statements about Calvin signal field. Okay, this is, let's say, an example of Calvin signal theory and nonlinear potential theory done directly at the PD level for nonlinear PDs, but you can still do this, and you will immediately see that also these tools like singular integrals, representation formula, maximal operators are not explicitly used. Their ghosts survive in terms of underlying ideas and methods. They are still there in one way or another. Okay, next part is non-uniformly elliptic operators. Okay. What are non-uniformly elliptic operators? Well, what is an elliptic operator? An elliptic operator is something that is, in the most basic setting, is defined by a matrix, and this matrix has positive eigenvalues, and this defines ellipticity. But on the other hand, the lower bound on the eigenvalues serves to obtain energy estimates. Essentially, these allow you, in the most simple cases, to invert the equation via Fourier transform. But the upper bound serves to control the estimates. So, in other words, when a matrix is called elliptic, where you have something like this, roughly speaking, and this is any vector in R3. It's a positive bilinear form. So this means, in particular, that you will have L, a bound like this, and a bound like this. So this is an upper bound for the highest eigenvalue, and this is a lower bound for the lowest eigenvalue. And then the ellipticity ratio is usually called as L over nu. And L over nu is something that enters all the constants in the estimates, in the sense that all the constants blow up when this guy goes to plus infinity and the estimates are lost. So in which sense the P Laplacian operator, also being degenerate elliptic in the sense that there is no lower bound, is uniformly elliptic. The P Laplacian operator, if you think of the P Laplacian operator, you have something which is the Laplacian, and then you have something, a coefficient, which is this one. Now, this is degenerate in the sense that when u is 0, then there's, let's say, this is the identity times 0. And of course, the lower bound. I need something to drink. One more. Too much choke, this is the usual effect. Okay, what do you get here? Is that although the lowest eigenvalue can go to 0, then the bound between the highest and the lowest eigenvalue is still bounded. So that's why Lagrangian and Rudolph they introduced for the equations we have seen in the first lecture these kinds of assumptions. You take the second variation of the equation, that is, you consider the matrix A of Z, and this matrix A of Z is bounded by something which is C to the P minus 2, and bounded from below by C to the P minus 2. So this is lambda squared. So when you do the ratio between this guy and this guy, you get back, and then the 2 simplifies, and although being degenerate elliptic, this is still uniformly elliptic. So the ratio between the highest and the lowest eigenvalue stays bounded, away from 0 and plus infinity. So the lowest eigenvalue goes to 0, but this means that also the highest eigenvalue goes to 0. Okay, now Calvin-Sigmund theory has been essentially, yeah.
I'm sorry, this is a condition on the derivative of A, right?
Yeah. Consider A to be, for instance, as in the P-Laplacian case, P minus 2 times Z. And then you can see that formally, if you differentiate, then you lose one Z, and then you get essentially Z to the P minus 2. These are the classical assumptions by Lagrangian and Rudolph that I showed yesterday. Okay? Okay, non-uniformly elliptic operators are now a class of operators for which Calvin-Sigmund theory is still widely open. And now I'd like to propose a few examples of non-uniformly elliptic operators for which a few Calvin-Sigmund type results can be obtained as well. Okay, in particular, these kinds of operators stem exactly as the P-Laplacian does from variational integrals. So we'll consider variational problems of this type. And the usual standard growth conditions are exactly these ones. So F is bounding Z to the P from below, and Z to the P is bounded from Z to the P from above. So these are the standard growth conditions the P-Laplacian operator belongs to and satisfies to. This is a classical example. Then there are no standard growth conditions, and no standard growth conditions are exactly described by those functionals that are controlled by a polynomial which is a higher power with respect to the one determining the coercivity properties of the function. So this functional is finite in W1Q, which is a space which is strictly smaller, of W1P, that is the one where the function is coercive. Okay. First of all, before going into Calvin-Sigmund theory, one should understand the type of operators and the type of functionals when modularity is there. And the classical condition due to Marcellini and then Giaquin and Marcellini by counterexamples is that Q cannot differ too much from P. Because otherwise minimizers are bounded. You know that minimizers of this guy. Yeah. N is the dimension.
So in a given dimension, Q and P can be anything?
In
a fixed dimension, Q and P are arbitrary?
No. There's a constant depending on the dimension such that you cannot go beyond that. For instance, a classical result is, if I remember correctly, this one, which is 1 plus 1 over n minus 2, and then you see when n goes to plus infinity, this goes to 0. Okay. In particular, this tells you that, in some sense, you see, if you get a function like this, then you know that minimizers are C1 beta for some beta, and this is not any longer the case when you deal with functionals of this type under PQ standard growth conditions. So examples. Okay,
So
this is.
So you really mean that there should be a tilde there, and or the below n in terms of doing what again? It's going to. It's a constant which tends to 1 as n goes to infinity.
Exactly.
Good, thanks.
Yeah, they are going to be closer and closer. Because you know that regularity is in some sense an effect of Sobolev embedding, right? And therefore Sobolev embedding deteriorates.
So what you mean is below 1?
When n goes to plus infinity, all of n goes to 0. You don't like the notation.
That's okay.
Yeah, okay. Let's assume that. Okay, let's assume that from now on, all n is defined by.
Okay.
Okay. So these are a few people that eventually worked at various stages under these conditions, but then there's a large literature of this on these non-uniformly elliptic operators. Essentially, one of the first examples was the minimal surface operator, because the minimal surface operator is not uniformly elliptic. And you will see that when you do consider functionals with no standard growth conditions, then these functionals, they have Euler-Lagrange equations of this type, which are non-uniformly elliptic. Why? Because when you do consider the second variation of the functional, that is the matrix of second derivative of f, that corresponds in the previous notation of the first derivative of a, then this satisfies these conditions. Typically, you get lambda squared here, but then you get z to the q minus 2. Because if f's k is like q, then after two derivatives you go as q minus 2. And if f scales from p from below, then the second derivatives, they go like z to the p minus 2 lambda squared. So what's the ratio? The ratio between the highest and the lowest eigenvalue is now proportional to what? To q minus 2, z p minus 2, which is c to the q minus p. So you see that the ratios are not bounded. And this, in this sense, is a non-uniformly elliptic. Essentially, that's a competition, because what you want to prove is that eventually the gradient is bounded, because after that you establish that the gradient is bounded, everything becomes easier, because essentially growth and infinity are not relevant anymore. But if you want to prove that the gradient is bounded, you have to exclude that it goes to plus infinity. But if it goes to plus infinity, on the other hand, the ratio between the eigenvalues goes to plus infinity. So the meaning of a condition like this is that the distance between q and p cannot be so large. And so this is a bound on the rate of non-uniform ellipticity of the operator. And of course, the mechanism that influences this condition is Sobolev embedding theorem, which is basic in regularity. And you know that the power of Sobolev embedding theory deteriorates with the dimension. So that's the underlying principle. Okay, in particular now I would like to show a class of non-autonomous functionals, therefore depending not only on the solution but also on the position with respect to the integral, and to show a new phenomenon that shows you how what is usually considered a perturbation when p is equal to q, so in the standard elliptic setting, is not any longer a perturbation in the setting of non-uniform elliptic operators. So essentially, this could be described as the absence of Schauder theory, or failure. Okay, why? Because you know that if you consider, for instance, this model functional, then you know that the regularity of minimizers depends strongly on the regularity of this coefficient, which is supposed to be elliptic in the sense that it's bounded away from infinity and 0. In particular, if you want to have that the gradient is Hilbert continuous, then you know that C is dimensionally speaking next to the gradient, so Cx must be Hilbert continuous itself. If you just want to know that the gradient is, let's say, Hilbert continuous with every exponent, then C of x must be continuous, and this implies that U is C gamma for every gamma. If you just pretend that Cx is just measurable, so it's real crap, then you get just C gamma for some small. That's the George's theory. And the first step is actually Schauder's theory. So in other words, the presence of a coefficient is a perturbation in the regularity. Now we will see that for when you couple the presence of x with the non-standard those conditions, then the presence of x is not a perturbation anymore, and this is a new phenomenon. And this is a new phenomenon that you can immediately see by looking at these functions. These are proposed in increasing order of difficulty. So, if you observe this functional, then these three functionals have one feature in common, that the rate of the polynomial growth with respect to the gradient is strongly influenced by the value of x. In the first case, if x is such that it belongs to the zero set of the weight w, then there's no ellipticity anymore. This is a degenerate functional. This is a prototype used, very much studied in the 80s after a paper by Felix Koenig and Serapioni. They observed that if you take a class of weights called Mackinac weights, then you can reproduce the theory. In the second case, you see, obviously, that if x varies...
So presumably, Mackinac means that the zero set can't be too big.
No, not really. Also, but there's a sort of rebalancing condition. I mean, if I remember correctly, Mackinac is something like, I don't remember well the exponents, but it should be something like this. I mean, it's AP if belongs to WX. 1 minus P minus 1 and P minus 1. And this is finite, super for every ball. This is AP, and then if it's AP, and then you have due to the P, then everything is okay. I don't remember if these are exactly the exponents, I think so, but it's okay. So it's a sort of rebalancing. If you're going to 0, then next, okay, this means that if you're going to 0, then you cannot go too fast to, when you go fast to plus infinity in order to recompensate the ellipticity you're losing.
So wherever the W is going to 0, it's also getting large somehow.
Yeah, it's a balance.
It's
It's a balance, yeah. Anyway, you formulate this condition, this condition you can do a lot of philosophy on it, but it is coming from the estimates, essentially. Okay, the second case is obviously clear, because if x varies, then p varies, and then the ellipticity of the operators, the kind of ellipticity of the operator changes. And then the last example that I'm going to talk about today is a newer one, and all these were proposed by Zhikov in the setting of homogenization and to model strongly anisotropic materials. And actually, the last functional is, I think, is most interesting because it catches the feature of the first two ones. Why? Because when a of x is 0, then this is p. When a of x is larger than 0, it's like q, but depending on how large a of x is, so it catches up both the feature of this guy in the sense that you change the exponents from one to another, but it can be also viewed as a sort of weight problem. The idea is that each one of these problems had its own Mackinac condition guaranteeing for regularity. Now, if you obviously observe that in these cases the rate of ellipticity depends on the point itself, you immediately understand that the presence of x cannot be dealt by perturbation methods. Because perturbation means that when you slowly vary x, nothing changes. If you slowly vary x, everything changes, and therefore it's easy to predict that no perturbation effect can be observed here. And that's in fact the first example that we got many, many years ago. Actually, the paper was finished in 2001, so it got so long to be published. And so this is an example that Esposito, Lorenzo, and myself built many years ago, and shows that you can make a choice of a Hilbert continuous exponent satisfying these things, but then a minimizer does not belong to W1Q. Because that's actually, if you want to prove regularity of minimizers, then the first thing you would like to do is to bootstrap the regularity from W1P to W1Q. Because a minimizer makes the energy finite. Since the energy is coercive in W1P, then it's finite in W1P. And then the first thing you would like to understand if it's in W1Q. And then the minimizer fails to be in W1Q. So you see, everything is very, very good. The Hilbert coefficient is good. You have two very nice things, but when you put them together, the minimizers break down regularity. And when things go bad, they can go really bad, because in an X example.
Sorry, come back for a second. The A here is it's not bounded away from zero, so it's degenerate, right?
Of course, it must be degenerate. Otherwise, I mean, it's standard Q grows and there's nothing. Here, the real point is the transition when A of X becomes zero. So everything. So it's essentially why these functions were used also in the setting of homogenization, because they want to make a model for two materials from classes of two materials.
Turning on and off.
Exactly. So A of X dictates the geometry of a composite made up by two materials with two different harmonic exponents. Okay, but I'm mostly interested in the regularity here. So essentially, the whole game happens when A of X goes to zero. If it's totally zero, it's trivial. If it's always larger than a constant, it's trivial, and otherwise it's not. So this means that, and these are the conditions that we found. So let me rewrite down these conditions here. So these conditions are the following ones. So as I said before, when things go bad, they can go really bad. And in fact, together with Irene Fonseca and Yamali, we proved that you can build up a scalar functional of the same type. A of X is as regular as you like. And then you can get, once again, this farness condition. But still you get a minimizer which is discontinuous. And the set of essential discontinuity point is a counter set of nearly maximal dimension. Nearly maximal, why? Because, okay, this is a set of essential discontinuity points. This means that these are the points where this is not going these are the set of non-Elliptic points. You know what is the threshold, the dimensional threshold beyond which you cannot go. If you are a W1P function, then the set of non-Elliptic points, the Hausdorff dimension of the bad set, is less than or equal to n minus p, because it has capacity 0, or p capacity 0. So this means that a minimizer of a strictly convex, smooth functional, scalar functional, can be as bad as any other competitor with respect to the regularity. Because essentially it is this situation. So both and actually we built an example where the set of essential discontinuity point was a counter set of maximal dimension. And this was done starting by a few constructions by Zhikov, and based on the fact that there was the so-called Lavrentiev phenomenon. Lavrentiev phenomenon is something that tells you that you cannot approximate the minimizer of a functional by taking the values of the functional itself on a dense space. In other words, this is a classical fact in the calculus of variations developed a lot by Lavrentiev, Tomedi, and others in the 20s. And this means that you see that this space is obviously dense in this one, but still the inf is larger than this.
So the functional is lower semi-continuous, but not continuous, or something like that.
It's genuinely lower semi-continuous. So it's strictly lower semi-continuous. Yeah, exactly. That's lower semi-continuity. It's exactly this. You can go below, so you find a minimizer.
Right.
But this tells you that you cannot really pick it up with the. Let's say, in other words, if you take the relaxed functional, making the smoother functional, then the relaxed functional is strictly smaller than that functional. It's a follow minimizer. Okay. Okay, what about the regularity? The regularity was a rather delicate question, and the only thing that we were able to prove at that time was this result with Esposito Leonetti that claims the following. That if you have a general minimizer, this is in the same JD paper from 2004, if you get these conditions, then a minimizer is in W1Q locally, but nothing more about the pointwise regularity. So this was essentially the result we got at that time. And so you see that these conditions are clearly failing in the situation of the counterexample. Okay, recently, together with Maria Colombo, we went back to this issue and then we established the following theorem, which is at this stage sharp. So actually the theorem is stated for this special functional, but it applies to a larger class of functionals that can be controlled by this functional, can be controlled and described by this functional. So take a minimizer, then the same condition that allows you to go to do the bootstrap from W1P to W1Q, then allows you to get that U is locally Hilbert continuous. This is sharp in the sense that on one hand, this is the best possible regularity you can get, because this is Ural-Severs theorem. When A of x is totally 0, you get just dv to the p, and then you cannot go beyond this for a certain exponent. And this is also sharp with respect to these conditions of the counterexample. Okay, but then we observed also that in the counterexample, you get a bounded minimizer. So the minimizer is discontinuous, but it's bounded because it has a bounded boundary medium, and then there's a maximum intrinsic. And essentially, the real sharp example is in this second theorem. Actually, it's the same journal, but there are two different papers. There are two different papers. So if the minimizer is additionally bounded, then the condition is relaxed in this one, so it's n-independent, and it's fulfilled really. It's really the one which is complementary to the example. So the example tells you that the distance between Q and P must be larger than alpha, and here tells you that if the distance is close, then you get the gradient is regular in the way you like. So these are the two sharp examples, and we also achieve the borderline case. And now this opens the way to the nonlinear Calderon-Zipfel theory that tells you that you have a perfect analog of this theorem of invariance. So you take the Euler-Lagrange equation of the functional. This is nothing but the Euler-Lagrange operator. Then you put on the right-hand side something which, for your pleasure, you write down in this form. The theorem works for any divergence right-hand side, divergence of f and blah blah. You just put it in this form as Ibanez did for aesthetic reasons, right? But the important thing is that on the left-hand side you have the Euler-Lagrange operator defined by a function. And then this tells you that any solution is as regular as the right-hand side allows. So this you can prove, provided you have the same conditions.
So you say you allow gamma to be equal to 1? That's so strange.
Gamma equal to 1 is trivial. Because this is finite. Yeah?
Yeah.
Gamma equals to 1, it's the trivial case. You want to improve. Because you already start with something which makes the energy finite, and the energy is finite because you have to start, and it's L1. So the point is that you want to get this larger, gamma as large as you like. And so this is up to now the strongest theorem about nonlinear Calvin-Sigmund theory for non-uniformly elliptic operators. The proof is very delicate, and it recombines a lot of ideas, mixing up P Laplacian and ideas for these double phase functions. These are what we usually call them, it's double phase functions. And moreover, if this is a bounded minimizer, then you can relax this condition. So you get the same result if you get a bounded solution. We have also an additional assumption that it's a Morley condition for this, but this Morley condition is not unnatural because this is essentially the condition that allows you to deduce that the minimizer is bounded, that the solution is bounded. So essentially, we can deal with these kinds of degeneracy, and I think this is a good place to stop here, because then tomorrow we'll describe a bit about, phenomenology of this double phase function of Calvin-Sigmund theory and so forth. So I think we can stop. It's not here. There are questions, remarks, complaints, appreciations, insults. No.